Hello community. I received a lot of questions about transformer-based reinforcement learning after you fine-tuned your LLM. So I ask you two versions. So what about code implementation? What about reward modeling, the dataset configuration? Do you want to see how we apply the code of PEFT? How we share layers? How about the Kullback-Leibler divergence between the probability distribution? Yeah, and you, my viewers, you here decided you do not want here the classical PPO configuration and the reward trainer, but you were interested here using the LLama models. So today we will focus on LLama2 model with code implementation for a transformer-based reinforcement learning. And of course, we will go with a 4-bit version. We will apply here some quantized LoRA. And I think let's dive into this. If you are new to my channel and you say, heck, what is reinforcement learning from human feedback? I ask here Bart, and this is the label that I generate. Say, hey, this was generated by an AI, this text segment. Reinforcement learning, let's start with this, is a type of machine learning where an agent learns to behave by trial and error. The agent receives some rewards for taking the actions that lead to the desired outcome, and the agent takes some penalties for taking action that leads to some undesired outcome. Over the time, the agent learns to take actions that maximize the reward function. And you see here, one of the challenges of this approach is here, define a good reward function for the system. This is not an easy task. Plus, and this is now the third step, we introduce here the human feedback. So we have reinforcement learning by human feedback. It's a technique that addresses the challenges of defining a good reward function by using human feedback. Steps are easy. The agent is first trained to perform a task without the human feedback. Then we have some feedback in the loop. We get a reward function and the agent is retrained with the updated reward function. As easy as can be. If you want to inform yourself, I have here a video about reinforcement learning in robotics. So we have a transformer model that is not based on a pure LLM, not based here on a vision language model, but based on a vision language action robotics model. In this video, I showed you if you want to code this in the classical transformer reinforcement learning way, and this is here by HuggingFace. I use here the code by HuggingFace, since in my opinion, it's one of the best code implementation you can find. We have here the Supervised Fine-tuning Trainer, then we have the Reward Trainer, and finally we optimize here the SFT model using the rewards from the reward model and a specific PPO algorithm. Now, people ask me, hey, what about the best code implementation? It's again, here you go to HuggingFace, transformer-based reinforcement learning, examples, research projects, stack Llama. So this here is the code implementation for LLama1. You go to the scripts and you have the supervised fine-tuning. You get it. You have the modeled reward modeling, and the third step is here on GitHub, the reinforcement learning training process where you have your PPO process. This is what you know. This is what I already showed you. Please note that there are continuous updates. So you see here the GitHub HuggingFace. What I told you, here are your 3 files that you need. Yeah, of course, we have a merge PEFT adapter, a Python file. So where you have your LoRA adapter weights that are then merged with the base model. And as you can see here, every 2, 3, 4 weeks, there is an update. So please regularly check out the code updates. Great. Now, I know a lot of you know about this. To be more memory efficient in the code for fine-tuning, you can share some layers between the model and the reference model. You know the code is simply here the number of shared layers you want to connect. Or if you initialize your reward model on the correct device using here our 03 context manager, these are the code sequences. You know this if you load here for a reduced memory footprint here, the model in 4-bit, you know the command, and please do not forget to optimize here your CUDA cache optimizer. Great. So this is the old, traditional, the classical model. And you know, when we have here a frozen reference model, that the new trained version does not deviate too much. We have here a Kullback-Leibler penalty, and you know that the Kullback-Leibler divergence is kind here of a difference between two probability distributions, but it is also known in theoretical physics as a relative entropy measure. Great. Yeah, if you are lucky, you are lucky. So I made this video yesterday, and after finishing the video yesterday on Twitter, what I found, there's now a new release of PEFT. So we have now an alternative, a new way to load and train our adapters here with PEFT as a backend, which is great that we have now an additional code base and we have changes to your code base. But never mind, I just saw it. I have not tried it out since yesterday. But look, it is rather easy. You have again your model ID, you have your auto model for causal LM from a pre-trained model. You have your classical LoRA configuration. And what is new is now the command model.addAdapter with your specific LoRA configuration. And you can give the adapter now a name. And yes, you guessed it, that the integration that makes it possible to load the base model and the injected adapter tensor structure directly using the transformer from pre-trained. Yes, 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 you know this. And the nice thing is now here that we can use multiple adapters and we can switch on adapters and we can switch off adapters in our model. Now, this is really interesting if you have multiple adapters. And I have not tried this out since it was published yesterday, August 28, 2023. But this is now a new way in your code base. So please keep in mind the brand new code you will see starting today, that you will have here this model set adapter, where you have set adapter and enable, and you get it. Great. As I've shown you, we are not going to use here the old reinforcement learning from human feedback like GPT-3 or GPT-4 was trained on by OpenAI with the PPO policy, where we build a reward model. No, we will use here from Stanford University, published end of May 2023, a new optimized procedure. So you're happy, you say, what? I do not need a reward model. I do not need a reward function to construct. Yes, this is the beauty here of direct preference optimization. A beautiful paper. If you want to read about it, this is the paper, and here you find the archive link. So here we go now. We do now reinforcement learning by human feedback with the new methodology, and we have a look at the code implementation with Python. And of course, as I ask my subscriber, you want already the LLama2 model, the code for the LLama2 model, and there was the majority said yes. So we will use here the base model, a LLama2 model, where we will use here a parameter efficient fine-tuning algorithm, and we will focus here on the quantized LoRA version by bits and bytes. We will use here 4-bit quantization, and of course, if you use here in the cloud multiple GPU or multiple nodes, we will use here the HuggingFace accelerate methodology for multi-GPU. Great. So what is new? You know that now we have only 2 steps here in our reinforcement learning from human feedback. The first step is the same like in PPO. We have our supervised fine-tuning. I will show you the code to load the base model and the 4-bit quantization and add the LoRA layers on top here of the quantized base model. You know this. The second step is now the new one, the DPO training. So we do not construct here a reward model, but after the supervised fine-tuning step, the model is saved and then used for our DPO training. For DPO, we need some specific human feedback data. So we need here a very specific data set. If you want to brush up a little bit your knowledge, this is the video where I explain what is PEFT, what is LoRA. I have a video where I show you how you can code and fine-tune the performance here with PEFT LoRA adapter tuning on a GPU. If you want to go to 4-bit quantization, I would recommend this video with the Colab code. And if you finally want to understand what is this new thing, this new DPO methodology instead of the PPO from OpenAI, this is the video to bring you up to speed. So, great. So we do something new today on a LLama2 model. We have here our two main steps. And as you can see, we have a HuggingFace library. HuggingFace, the best place to go, where we have our two steps. So we just say, hey, accelerate launch, and then we have a script, and we have here the supervised fine-tuning of our LLama2 model. It is already a Python file. Couldn't it be easier? And to run the DPO-Trainer using the model, we have here also a command where we have the DPO training on the LLama2 model. This is it. But hey, suddenly we have here from an autonomous AI agent who says, hey, stop, wait a second. You are using terms you have not explained. So, as you can see, a lot of you ask me, what is a task of an agent? For example, here, giving my presentation, an agent listens to this, but whenever I use terms or explain here, or use here a methodology and I do not explain the methodology, an agent who is listening to me might say, hey, stop. You forget here to check for consistencies and that I explain every term and every method that I tell you. Great. So let's do this. And the agent might say, hey, you told us in your last video how important it is to choose the perfectly designed dataset for the fine-tuning. So you remember in this video about fine-tuned wizard coding LLMs, I told you that the performance difference between the classical code Llama in the 34 billion free trainable parameter version compared to the wizard coder with the same model size is 20 points. And it was primarily achieved by a clever high-performance fine-tuning dataset. So we have here the same question. What is the perfect dataset here for this new DPO method? How should we structure our dataset? What needs to be in the dataset? Is there something to watch out for? And of course, since we are talking about reinforcement learning by human feedback, we need human evaluated data. And I know in the last videos I told you how cheap and fast it is to generate synthetic data, especially from GPT-4. But now when we have human feedback, we need human data. Now, you can have a lot of crowd workers or whatever you like to call, where people sit down all over the world, open their laptop, and have some exercises, some micro jobs given by different platforms where they do provide human feedback. But we have to be careful because this human feedback might include polarization or some nuances of opinion, either some ideologies or some cultural differences, because you know what? We have 195 nations on this planet. And each nation has a different cultural, has different values, and has a different perspective how to see this. And all of this, let's call it polarization or a nuance, is inherently unconscious in the human evaluated data. But when you bring back here the response from 195 nations, you will get not a clear, homogeneous human opinion data set. Now, the answer is rather easy because we use here platforms like Stack Exchange. What is Stack Exchange? You see here their homepage. So you as a user have a question. I don't know, is philosophy bad for you? Or, oh no, what movie is this avocado-like monster from? No idea what they are talking, but you see you have one question and you have 15 answers by a human. And currently, in August 2023, we hope that those answers are really by humans and not already by AI bots. So, you have here Stack Exchange. And the beauty of Stack Exchange is they have a lot of segments. You know, if you work in Python, Stack Overflow. Here, a beautiful platform. I learned Python participating and reading here the answers from experts in Stack Overflow Python. Or you go here for mathematics. Or you go for graphic design, database administration, cryptography, computational science, sustainable living, whatever. So we have platforms and we have questions and we have a lot of answers. And those answers are rated because there is a best answer voted by the community. And this is great. So we have a human feedback on really millions and millions of questions. Now we go to HuggingFace, and you see HuggingFace H4, we have the Stack Exchange dataset. And here, for example, we have 10 or 11 million rows, and you have here a typical dataset where you have exactly this. You have one question and you have, let's say, 10 different answers by the viewer, but the community rated those answers, so we know what humans preferred as the right answer and what humans did not prefer. And this is great. So you see, size of downloaded dataset files close to 20 gigabyte. 10.7 million instruction. Great. Now, when we work with DPO, we need here a specific format. And great, Leandro van Vera was so nice to provide us here. And you see a HuggingFace, Leandro van Vera, Stack Exchange paired. This is a data set that has been created exactly for the job that I want to show you, DPO. So what we have a question. Let's say this is our first question. And then we have answers that are good and answers that are bad. So we have, let's have a look here at this place, a response J and a response K. So below a threshold and above a threshold. And wherever you go, you will see here exactly this is the pattern that we have. So response J, response K, and a specific question. So we know exactly what we want, or what the community wants and what the community does not want. Isn't that great? And if you ask how you come here from the general Stack Exchange structure to this specific file format and data set format, Leandro was so nice. And if you go here under files and version, you have here his Stack Exchange processing. You have here his Python notebook where he exactly shows you how the thing is done. I copied this notebook here simply as a generator when I have a generic data set to make absolutely sure that I have the right data format for Stack Exchange if I want to use it with reinforcement learning for human feedback. And you might say, great, so now let's finally code together. Yes, as I told you, this is a video you might be interested. So here we are. The dataset preparation is important. As I showed you, we have a prompt. This is our question. And then we have two categories, the chosen answers and the rejected answers. So we have here, for a given question here, a human feedback. This is what we want and this is what we do not want. Isn't this beautiful? Yeah, this is the code from the Jupyter Notebook. So let's start with the first part, and I show you here the core of the Supervised Fine-tuning, SFT. What we do, I told you, we will load the base model in a 4-bit quantization version by bits and bytes. This is done here beautifully. Then we have our normal base model defined by AutoModel for causal language modeling from a pre-trained version. we will use here the LLama2 version. We will use the 7 billion version by HuggingFace. Then we will add the LoRA layers on top of the quantized base model, where we have here simply a PEFT configuration file, where we have all the hyperparameters of the LoRA configuration, of the low rank adapter configuration, of our matrix or tensor approximation that you know, that you love. And finally, we have here our trainer module. This is our supervised fine-tuning trainer module. There we have our base model that is quantized here. Great. There we have the training data set and the evaluation data set, as you know from fine-tuning any LLM. We have here the PEFT configuration that we defined here with our LoRA configuration hyperparameters. And this is it. And then we just start trainer.train. So we start training our model by calling the train method on our training script by HuggingFace. All the code by HuggingFace, go to HuggingFace. This is my preferred source of information to learn code implementation. Yeah, this trainer supports the native integration with PEFT, so everything is taken care in this core segment. Super easy to efficiently instruct, tune your LLMs. You just need to create your LoRA configuration and provide it to the trainer, and the training happens. The second main part, and this is the most important part, is now the DPO training algorithm. Great. As I showed you, we do not construct a reward function. We do not construct here reinforcement learning. But what we have a model and a reference model. And you're not going to believe it, it is more or less what we just trained. So we have here now our auto-PEFT, careful, auto-PEFT model, because we used PEFT for causal language modeling from pre-trained. And you indicate exactly the location where we just saved our supervised fine-tuning model. Then we have the model reference and our DPO-Trainer. Now our model trainer gets as parameters, of course, the model and the model reference. Then we have a lot of hyperparameter training arguments from the, I don't know how many epochs and whatever you know. This is the classical stuff. We have the training data set, the evaluation data set. You define the tokenizer and the PEFT configuration. And again, you say, hey, DPO-Trainer.train, run, go. And of course, you can save the complete model. And since the models were trained with the LoRA adapters, we load the models via the PEFT auto-PEFT model for causal LLM helpers by HuggingFace. Great. So these are the two core elements, and you see they are similar. The script is really beautifully written. And if you want now to have a deep dive in the complete code implementation, look, both files are available for you free of charge. GitHub, HuggingFace, TRL, blog, main, examples, research. I leave you the link here to the supervised fine-tuning of LLama2 and DPO training for the reinforcement learning by LLama2 in the description of this video. So why not have here a look at the specific Python file? As I just showed you, stack exchange dataset on the LLama2 model, and we apply every trick that we know from the book to keep the memory footprint down. So first Python file is here the supervised fine-tuning of our Llama model with here the specific stack exchanged paired dataset that Leandro von Werber prepared for us, publicly available on HuggingFace. So let's dive into this, and you know this, you know everything. We have PEFT, auto-PEFT, model causal, LLama, the LoRA configuration. From the transformer, we have the normal auto model for causal language, the auto tokenizer, the bits and byte configuration. You know everything. Yeah, of course, we have the SFT trainer here from HuggingFace, from the transformer-based reinforcement learning. And then we have a lot of scripts argument. And here, as you can see, default is by Meta Llama, the LLama2 model in the 7 billion version, already adapted for HuggingFace. And as you see here for your data set, now this is the data set I want to show you, is here exactly what I just showed you, Leandro van Vera stack exchange paired. So we have here the default data set. If you want to see this training here, everything is already there with default values. You just hit run and it will perform for you. Okay, arguments, you get it, you can read it yourself. This is no problem at all. You have your trainable parameters, you prepared a sample, you create here the data set. This is standard. We don't have to look at this anymore. As I told you, we go for a 4-bit quantization. So we have our bits and bytes configuration, and we just say load in 4-bit equal true. And then we use, of course, for the base model, our auto model for causal language modeling from a pre-trained version. And as I just showed you in the script argument, that we will use LLama2 model. If you say, hey, I want to use something else, please go whatever model is available on HuggingFace transformers. Great. The PEFT configuration, as I showed you, our LoRA configuration, our hyperparameters. What you know, this is the standard way to continue. And then, of course, we need our tokenizer, our auto tokenizer from our pre-train, and we have the model name, and we have to set trust remote code equal true. Beautiful. And then we have it. Here is our supervised fine-tuning trainer module, and we have as a model our base model. We have our training data set, our evaluation data set. We have the PEFT configuration. We have our tokenizer, and we need some training arguments. And here we have now our training arguments in the script. My goodness. So you go from a variable learning rate, a logging step, the maximum steps, the learning rate scheduler type to the warm-up steps. You know this. So whatever you want, please go to the script here and implement your specific data. As you can see here, we have for the number of warm-up steps 100, for the weight decay we have 0.05, optimizer type, yes. Whatever you want to modify, please do it here in the script arguments. Yeah, and this is it. And here the most important command, train our trainer module or a supervised fine-tuning trainer model, train, go, and then save the model. Beautiful. To remember, as I told you, our CUDA cache, empty the cache. And then you go here with the model that you know, model.merge and unload. This is exactly where you have your LoRA adapter tensor weights that you fuse now together with the base model. Isn't this beautiful? So this is the first one. And as I told you here, we have everything by HuggingFace available. HuggingFace here, transformer reinforcement learning. And now the second is here, maybe the most important Python file, our DPO-LLama2 Python implementation. So again, we have here everything the same. Then we have here our script arguments. Now you are familiar with this, you know everything, you are now an expert on this. Learning rate schedule type, warm-up state, weight decay, you know this. Yes, the default maximum length, maximum steps, save steps, evaluation steps. Okay. Get stack is exchanged. Paired data set has been done. I just showed you. Again, good reminder here in the data set here. Says, hey, the data set is converted to a dictionary with the following structure. You know now that we have here the prompt. This is the question in the Stack Exchange platforms. Then we have a chosen answer. This is the right answer with a high top rating. And normally there is about for one question, for one prompt, up to 10 answers that are very good, okay, acceptable and not acceptable, and rejected. You know exactly those are the human answer that we do not prefer. So we have here a positive example, we have a negative example, and this dataset structure enables the model to know exactly what we want, in what form we want an answer, and in what not form we want an answer. For example, as I have seen short time ago, there was a question about, hey, in family and you have, or if in a relationship, and you have the man and the woman in a relationship, and there was the question, what exactly is here the relationship between a man and a woman? And now you're not going to believe it, but some cultures, some nations on Earth, and we have 195 nations on Earth, including the Vatican, that based on their culture, based on their belief, based on their traditional norms, based on what they see from their parents, the position of a man and a woman in a relationship is specific to the cultural past. Let's formulate it in this way. So, if you want here in your LLM to have a specific nuance to a specific cultural region, to a specific historic relation, to a specific I don't know what social norm, this is exactly where you input your data so that the final LLM reflects here exactly here the examples given, and then you can have nuances in your LLM that are based on the examples you provide here in the reinforcement learning by human feedback. This is really the fine-tuning of the fine-tuning here from the human nuances to have a specific characteristic, a specific behavior in the answer of your LLM. Gee, this was a long explanation. So the prompt structure is then as follows. You load the dataset, you know, Leandro von Vera, stack exchange paired. I just showed you here on HuggingFace. It just connects, get it, beautiful. Where does it get interested? Yeah, you know everything. You know auto PEFT model causal from pre-trained, it is the same. Pre-trained, we have here our model, we have here our reference model, and we have our standard tokenizer. Second step is here, then we load the stack exchange paired dataset by Leandro von Vera. Great, we load the evaluation dataset. You're not going to believe it's also by him. And then you initialize your specific training arguments, because we will need this for the DPO-Trainer. So you have, I don't know, learning rate, evaluation steps, the output directory where everything will be written to, the warm-up steps, the learning rate scheduler type, everything that you need and want to specify for our DPO-Trainer. And as I told you, we operate here with a PEFT configuration with LoRA. Here you have your hyperparameters that you would like to focus on. And here, finally, the fifth step, initialize the DPO-Trainer. The DPO-Trainer here in its beauty is already coded for you by HuggingFace. So this is great. So what we provide to our DPO-Trainer, of course, the model, the reference model, as I showed you, and all of the training arguments from whatever parameter you want. Of course, as I showed you, the script arguments that we had at the very beginning. Then, as always, you have a training data set, you have an evaluation data set, and you have a specific tokenizer that breaks down here the human, let's say English text, into specific tokens. You have your PEFT configuration, the maximum length, yeah, everything. And the final step, of course, is DPO-Trainer.train. And here you go. This is our DPO-Trainer. This substitutes here all the reward function, all the reward model that was done in the old case by OpenAI with GPT-4, for example. Here, Stanford University proposes here this specific model, and following their evaluation, they say that this has a better performance. Is a better performance always true in all circumstances, on all user cases? I don't know, but in those applications that they tested, that they evaluated, it seems that a DPO-Trainer has a lot of advantages. You do not have to construct reward models. You have less time on the machine for those exactly fine-tuning of the reward function, and finding the perfect reward function for your specific downstream task is not an easy task. yeah, you save it and it is done. So here you have it. 2 simple Python files to do everything that you want to do. So we are back here to the very beginning where I showed you that I have here the request by my subscriber. Hey, show us here the code to have here reinforcement learning by human feedback on a LLama2 model. And let's not just build here the classical PPO, but let's go with a DPO on the LLama2 model, 4-bit quantization, LoRA, every trick that we know out of the box. How is the code? And you see the last code optimization was performed here just last week. So this is really a directory I would recommend if you would like to see this. And I've also showed you if you have another data set, then Stack Exchange dataset, you have your corporate dataset, you have your private dataset, whatever. There is this Python notebook where you can transform almost any dataset structure in the necessary dataset structure to have here the perfect data format for our DPO-Llama2 training algorithm. Long video, I hope it was informative. You get some ideas. I will leave you the link to this in the description of the video. And I hope you enjoyed it. It was informative. It would be great to see you in my next video.